And you're almost done?
Gladly, yeah.
Yes. All right. So is there a participant count here?
46.
I see. Okay. Oh yeah, 46 at the top. All right. Well, see, it's 14:30 Pacific time, so we're ready to start the meeting. I'm Dave Plonka, and Mirya Kulabind, the co-chair, is also on. This is the Measurement and Analysis for Protocols Research Group at IETF 111, meeting online. If you need to contact us, Maprg chairs at IETF.org is up on the screen. Otherwise, you can write to us individually by those addresses. Okay, I clicked 2, and it didn't go to the second.
Slide. No, I see it, yeah.
You seeing the second slide? I'm not.
It's not great, but just go on.
Well, I can't. I have to see what it says.
It's a note well.
Okay, so the note well for intellectual property is similar to that for the IETF, but read it in detail, please, if you're sharing any work that might be covered by intellectual property restrictions by either you or your company. Slide 3, which again I can't see, but I know is the privacy and code of conduct portion. So you can find details on slide 3 of the chair's intro slides. Can you see them, the rest of the participants? Can you see the slide?
I stopped you. I'll try to share them again, and maybe then you can see them. Let's try that. Okay.
I can see the first one.
Now I'm on slide 3. No?
I don't see it on the screen, on my screen.
That's weird.
I don't need to. I mean, I have them up on my phone right next to me, so I guess I can muddle through it with that. If you see me making a mistake.
Try pressing the presentation view top left of the icons on the top row.
Yeah, but you can see still the first slide, right? It's just it doesn't move for you.
Yeah, I saw the first one.
That's weird. I now share the slides and I can click to the next slide. You do the talking.
All right.
Or whatever.
So we're on slide. So we just did the privacy and code of conduct as a formality.
Okay. So we go to
the goals of the IRTF. I'll let you read those details. They're in your copious free time, but we're not a research organization. I'm sorry, we're not a standards development organization. We're a research organization, so we don't have some of the same restrictions. And consequently, you might see a broader set of topics in the IRTF than you do in IETF working group meetings. Next slide, slide 5.
Yes.
Our charter is linked at that link. Maprg is meant to share nascent, usually nascent research measurement work about protocols that are designed and or operated under RFCs and decisions made in the IETF. So that's what we focus on, and we prefer, if you saw selections, we prefer submissions or contributions that responded to our call for comments. You might have seen in the mailing list, we had one candidate participant that happened not to respond to that. And so we do that as a sort of a form of equity between submitters, so that we expect you to respond to the call. And we sent that person a personal copy of the call to which they did not respond, but would be happy to have them in the future if they'd like to. Mailing list and the slides links are up, Meetup and Jabber. So next slide. We hit the IB workshop slide now. Okay.
Yes.
So the IB is holding a workshop on measurement network quality for end users. It's coming up in mid-September, 14th through 16th. There's a submission deadline coming right up on Monday the 2nd. It says midnight anywhere on Earth, which I believe means anytime during that day on the 2nd. So submit to that if you're interested, or watch for participating in it coming up in September. It's certainly on point for people that would be in Maprg. Go ahead, Maria.
So for IB workshops, what we usually need, these are invitation only, so we need to submit you a short position paper in order to participate. But it doesn't really have to be a big burden, and we just want to know like what your thoughts are and what your interests are, and then we can have you at the workshop if you want to.
Thanks, Maria. And then, so let's switch to the agenda slide. We've got a tight schedule, but these have worked well for the past 3 or 4 meetings. I'll try to keep us to the times of day listed in the agenda there, so I apologize in advance if I have to interrupt you to tell you how much time there's left in your segment, but please bear with me and help me keep that time so it's fair to the latter participants. We're going to have measuring shutdowns and more from Matt Ford up first. Then we'll have Matt, you're welcome to share your slides if you can. And then we'll switch to Jan Ruth about Quick and IPv4. And Nicholas Kuhn is joining us to talk about feedback from using Quick's zero RTT BDP extension over satellite communications. Oliver Gasser will come up after that with some multipath TCP measurement stuff. And then Jason Livingood and one of his collaborators, who I think is possibly the first author, Sebnem, is joining us on comparative latency under load performance of broadband CPE. Anything I forgot? Are we ready to get going? If there's no complaints yet, let's go to Matt. Matt, let's see. You're granted, I think, there. And I'll let you know if there's.
Dave, I hope you can see my slides.
Actually, I can't, but I don't.
Well, okay, maybe Dave can, maybe others can.
Started the timer, which is now running at the bottom, if that's helpful for you guys.
All right. And I'm assuming other people can see the slides.
All right, great.
So
thanks very much to the chairs for agreeing to accept this presentation. It's more of an infomercial in the spirit of a lightning talk than perhaps some of the more detailed measurement research that is on the rest of the agenda. But I wanted briefly just to use this opportunity to explain some of the rationale and the reality of a new resource that the Internet Society has produced recently called Internet Society Pulse. And I subsequently realized that, of course, I didn't put the URL on this slide, but if you have a web browser open and you go to pulse.internetsociety.org, you will see what I'm talking about. So briefly, why are we doing this at all? So the Internet Society has to engage with quite a broad spectrum of stakeholders in terms of folks interested in the evolution of the Internet, the governance of the Internet, and so on. And really what we wanted to try and do was bridge what we perceive to be a gap between a lot of really excellent and interesting measurement research that tends to be the meat of the agenda at meetings like this one, and what I'm sort of broadly calling non-scientific audiences. And that's everything from journalists to public policy makers and their research teams to other researchers in different disciplines and so on. And we wanted to be able to provide a trusted source of information about the Internet and the aspects of Internet evolution and growth that we cared about, and really to provide a resource that could help inform and support other projects and this sort of diverse communities of interest. So that was a sort of broad, high-level goals for this effort. What we're doing in terms of bringing data and an application to that is trying to essentially curate trusted third-party measurement data. So we're not really, in most cases, generating any new measurements ourselves. We're trying to forge partnerships with folks that do have data, and then curating is a nice word to use. Essentially, presenting the aspects of that data that we at the Internet Society believe are most relevant to the kind of topics that we want to talk about. And we want to use that data to examine trends over time. So longitudinal studies are very interesting, generating reports, and ultimately be able to tell data-driven stories about the Internet, how it's changing, how it's evolving, and so on. And of course, it's a website, so it's available to everyone everywhere. That's a broad topic, right? Internet measurement and bridging gaps and all the rest of it. We're trying to sort of narrow down a bit on that. And I've talked a bit about topics that are interesting to the Internet Society. So we're developing these what we're calling focus areas. The two that we have launched with and the two that are on the website now in the most detail are both Internet shutdowns and enabling technologies. We'll shortly be launching focus areas on internet centralization and internet resilience with a focus on Africa. And then we also hope to launch later this year, probably in Q4, country and region reports, because those are tools that we think will be particularly useful to policymakers who are interested in how their countries compare with their immediate neighbors or regional averages, for example. We are doing this entirely thanks to the support and partnership of quite a diverse range of organizations, and we're certainly very keen to add to this list of data partners. And so I want to just take a minute just to say thanks to these folks, because none of this would really be possible without their help. Briefly, the focus areas are, as I mentioned, internet shutdowns, where we're trying to curate a database of shutdown-related events. On that page, you can see a map that shows some visualizations of the intensity in terms of the number and the duration of shutdown events and where they occur. How they look on a sort of timeline. You can search by the location, the type of shutdown, and so forth. You know, over time, we're hoping to populate this essentially with snapshots of data that evidence the fact that shutdowns occurred. So we're very dependent on partners like UNI and the Center for Applied Internet Data Analysis and Access Now. We're very much focused here on shutdowns where we can point to evidence, either because the government said they shut down the internet or other partners said that they were ordered to shut down the internet, or where we can see that, you know, there was clearly an outage of BGP, or, you know, traffic to prominent websites, for example, was blocked, and that kind of thing. We're very much trying to provide this sort of data-driven side of when and where shutdowns occurred. And for each of these events, we provide a more detailed page where we try and identify relevant media coverage, related blog posts, and so forth. Possibly of more interest to this audience, we have a focus area on enabling technologies, which is basically anything that we think is really contributing to the future scalability and trustworthiness of the internet. And at the moment, we have data on IPv6, TLS 1.3, SEC, HTTP3, and HTTPS. We want to add to that list of technologies over time, and so I'm personally quite interested in any feedback on what, you know, technologies would be good to add to that list. You know, as I say, you can browse that page and look at the data there. It's really to try and convey some of the information around per country differences in relation to these technologies and how they're evolving, regional differences, and the longitudinal sort of you know, differences in terms of whether or not these technologies are rolling out, you know, seemingly quickly or perhaps less quickly, like IPv6. Where, as I mentioned, we're about to launch a focus area on internet centralization, which is I know is a topic close to some people's hearts. There have been workshops and such on the topic, and we are including analysis of 7 different technology markets as part of this, looking at 2 different metrics of centralization, and we're tracking those over time. There's a lot to unpack in this. I have no time now to do that, but it's just to sort of whet your appetite for this focus area that will be coming up, that will hopefully be of some interest to folks that are, you know, sort of curious about how when people talk about internet centralization, how can we sort of break that down? How is it evolving over time, and what does it look like?
Matt, you have 2 minutes. 2 minutes.
Okay, thank you. I'll get done in that time. The other focus area we plan to launch this year is internet resilience. We have a sort of a definition of internet resilience. We're looking to combine a lot of different metrics into an index of resilience, and we're building that out in partnership with Afrinic, looking initially at Africa, because I think we figured that if we can do anything useful in Africa, given the kind of infrastructure that's deployed there and the kind of data that we have about it, then we can probably do something useful anywhere, frankly. So look out for that later this year. That's particularly intended to help us engage the regulatory community in that region, in that continent. The sort of takeaway message from my talk really is that we're very interested in feedback on this tool. It may, you know, as I say, the audience for this is pretty broad, and it's certainly broader than the folks in this room. But you know, if it's useful to you, if you think it would be useful to you, if you have data that you think you could contribute, be very keen to hear about that. And on I think my last slide, there's a bunch of ways you can get in touch with us. So we have a presence on Twitter. We have an email alias where you can just drop us an email with any comments or questions. The website, as I mentioned, is pulse.internetsociety.org. We produce a monthly newsletter, which basically is a wrap up of what's new on the site in the last month. You can sign up to that on the website. So yeah, thanks for listening to my infomercial about Pulse. And as I say, we're very keen to get any feedback or questions you might have.
Thanks a lot, Matt. I didn't see anyone in the queue yet, but in the chat, Martin Duke asks a question about your internet shutdown slide. I guess about scope. He said, by internet shutdowns, do you mean legal authorities, not DOS attacks, or is it any kind?
Yes, exactly. It's I don't have the definition in front of me, but it is, yes, it is not DDoS attacks. It's not ransomware. It's very much the government mandated shutdown that we're looking at there.
Okay. All right. Thanks a lot, Matt. Yeah, if you could stop sharing that, and we could bring up next Jan Ruth's presentation. And Matt, check in the discussion thread. There was a couple people at least voting for wanting to see more centralization covered. Okay, Jan, are you ready to go?
Yeah, sure.
Okay. Proceed.
All right. Yeah, welcome everybody. So today I want to show you the deployment of Quick in IPv4, and also how you could get there or get at least to HTTP3 via HTTP headers and via the DNS. Okay, let's get started looking into the deployment in IPv4. What we basically do is we run periodic ZMAP scans to the whole IPv4 address space on UDP port 443 on every Thursday. And what we basically do is we send a quick initial packet that has a reserved version, which basically follows the pattern that you can see, and you can basically see the scheme on the right. And what's supposed to happen is that that version is not supported with Quick, and Quick should answer us with a version negotiation packet indicating the version it supports in case, well, it does. So we have been monitoring Quick since 2018, and we've been updating, or at least try to update to the drafts whenever they got released. So we have quite a nice picture how Quick evolved in the time during the standardization, and well, how the deployment on the intent looked like. What you can see here is the deployment in 2019. I split it into two plots because, as you can see already by the y-axis, the deployment is quite flippy depending on which versions you see. So what you can basically see is here that around February 2019, we have roughly 3,000 IPs that announce Quick support, and what you can also see in the legends and the different colors. There are different versions of Quick being deployed and tested on the internet. We can also see very specific versions from some well, manufacturers or implementers like MoveFast from Facebook. And what you can also see then, if you look to the plot on the right, is that there are that we have off and on phases where larger parties activate their Quick servers over time and then stop them again. It of course also depends a little bit when we updated our scanners ourselves. But what you can see is that by the end of 2019, we have roughly 750,000 IPs that claim to support Quick. In 2020, things got a little bit more involved, which you can also probably guess from the legend that you can't read. What you can basically see here is that people really started experimenting with a lot of different versions over the year. and which basically reflects the standardization of Quick, where we see a lot of drafts being put out and a lot of different versions being actually experimented with on the internet. Well, and what you can see is here at the end of 2020, we roughly have 1.6 million IPs that support Quick, and in 2021 we don't see a lot of change. What you can see is that we have a bit more, like 2 million IPs now supporting it, and maybe the most interesting one is if you start looking at the RFC 9000 line. This is the point in time where the RFC was actually released for Quick. And you can see roughly a month before, we start to see the first Quick version 1s being actually deployed on the internet, even though the RFC wasn't out that. But after that, we can also see in the brown dashed area that there are more Quick version 1s, but from a different implementer being rolled out on the internet. And today, it has already the largest share of those versions being supported on the internet, but there are still some other pre-RFC versions being, well, at least deployed. When we look at who's actually deploying Quick, here's basically the autonomous systems from which those IPs are coming from. What you can basically see is here in the top, I don't know, 4, we see the people that we actually would think we would see, like the big CDNs, Cloudflare, Google, Akamai, and Fastly. There's also Edgecast a little further down. We can also see some regular network service providers, but of course also Amazon. And if you go down that list, you find even more like Facebook. But basically here is just the top 10. So this is what we find on UDP port 443. But the question is, how would you actually know that you should have been connecting there? And from the start on, most people actually deployed on 443, but that isn't mandated anywhere. So the question is, if you have like a web server running on top of Quick with HTTP3, how would you actually get there? There are actually different mechanisms, and one of those mechanisms is the alternative service header in HTTP that you can actually use, where you can basically tell the connecting client that there's a different service, for example, via Quick available. And what we here did is we grabbed all domains from the .net, .org, and .com zone files, and we requested the root of those sites at the www.domain.tld. And what you can basically see here in that table is that there we have roughly 8 to 10% of hosts actually using, or at least of those that actually answer to our HTTP request, actually using this header. When we look further into those headers, here at the example of the .com zone, you can see here the counts of protocols and ports that are being announced. What you can see here is that most of those that actually use the alternative service header actually announce some version of HTTP3 with the -27. It basically means it's draft 27 and so on. So as you can see, this header is actively being used on the internet to signal Quick support today. This is not the only way today that you can actually use to signal Quick support. There's a quite recent draft to do that over the DNS with HTTPS records. I think it's a year old now. We did quite similar. We also got the zone files, the domains from the zone files, and we requested the HTTPS DNS record again for those domains. What you can see in this larger table is basically the same information as before. In the second row, you can see those, or the number of domains that actually give us a record, which is quite a lot, I would say, 2 to 3%, given that it's only a year old. And from those, you can see that most actually also give us an ALPN, which is the protocol and the version. The protocol identifier. And what you can also see is here that most actually claim to support HTTP2, and roughly, depending on the zone file, 55 to roughly 60% show some version of HTTP3, which has Quick underlying. Again, we actually found one ALPN that claims H3 in the .com zone. We also looked at the IPv4 hints, which is basically a mechanism where you can directly given IP address, which you could use to connect to one of those servers that support this protocol. What you can see is here that most actually give us an IPv4 hint, but the IPv6 hints are a little bit behind. If you look into this data, you will find that actually one of the driving implementers is Cloudflare that has a quite large share of sites where it actually announces these HTTPS records for. Yes. So this already brings me to the end. Yes. So what have you seen? Quick has been developed and experimented with on the internet quite extensively. We found different implementers. We found a continuously rising deployment over the past years, and today Quick version 1 already dominates those versions. There are a lot more parties involved than with gQuick before. There we also the Google version of Quick. There we mainly found experiments on the public internet from Google and Akamai, and now we see a lot more parties involved. And regarding the different mechanisms, how you would discover these services, we found that the alternative service header in HTTP is, well, fairly deployed, 8 to 10%, and most of those actually show some version of HTTP3. There's also already some support for this DNS HTTPS record. And that's it. Thank you very much.
Thanks for bringing this to us, Jan. We have
Sure.
Martin Duke in the queue to ask a question.
Thanks, Jan. What's the significance of the 18-byte connection IDs in your quick graph?
Oh yeah. Let me skip back. Yes. I'm not quite sure how many bytes we used before that date, but as far as I remember, Dimitri, I forgot the last name, from Lightspeed contacted us.
Tikhonov.
Yeah, exactly. That his IPs weren't being picked up by our scanners, and he suggested that we should use longer connection IDs. And as far as my tests, I mean, it's quite a year. It was a year before now. As far as I remember, I think we didn't get some Google servers when we used shorter connection IDs, but I'm not 100% sure.
That's interesting because the spec says that a server should accept an 8-byte connection ID for its initial packet.
That's also, I think, before we changed it because there were some changes from 2019 to 2020. There were some new drafts coming out. I think I changed the scanner to actually use only 8 bytes because I thought, why spend all those bytes? But that showed some worse results, so I switched to 18. But
I do wonder if this is an encoding issue.
Guys, I'm going to interrupt you. Could you take this offline or to the to the chat? Thank you so much. Just because we only have 5 minutes on balance to deal with picking up here. And if you're interested, Luke, I see Lucas Pardue added a comment about a Cloudflare blog post of HTTPS record that is probably pertinent here. So can we get, thank you so much, Jan, for bringing that. Can we get Nicholas's slides up? All right, Nicholas, are you ready to go?
Yes, can you hear me?
Yep, we can hear you.
Okay.
You got it, go.
Okay, thank you. Thank you everyone for giving us the opportunity to present the work we have been doing on basically trying to test the zero-RTT BDP extension for Quick over public SATCOM access. So this is Nicholas speaking, and this is a conjoint work with Emile, Gori, Tom, and Christian. Basically, there are too many content on these slides and only have 10 minutes. The main idea was to have slides with lots of contents so that anyone can just read at it later on. The main point of this slide is that basically we are working on Quick over satellite links, and our satellite links have a very high delay and a non-negligible capacity. So we have a very large bandwidth delay product, making it hard for congestion control to actually reach the available capacity. we are always interested for anyone who has the same issues that we have. We think that there are lots of cases where the BDP is high, and we think that our approaches could help them. Basically, what our extension is doing is that basically during a previous connection, you record the RTT and the bandwidth delay products of the connection, and you share them when you want to resume a connection. So basically, it's all about exploiting previous connections characteristics when you want to resume a new connection. We think this could be useful for other use cases than ours. You could optimize client requests, you could do safe jump, and you could also share transport information across multiple connections. Here, before going up into the results of the zero RTT extension, I think it's important to recall quickly some results. These are all the details of the experiments we have been running. They are the link with a platform that has been exploited, and we have been using Pico Quick implementation with BBR. And basically, we change the RTT and we download different file sizes for different bottleneck link capacities. I'm not sure if it's clear on your slide. On your hand, I realize that on my screen it was, and on the screen I'm seeing now it isn't. So basically, I may not spend too much time there. The main point that we wanted to say with this slide is that sometimes, because I'm working for a geosatellite world, it's important. It is important for us to recall that sometimes when you have a very low capacity, basically the RTT does not have a much impact on the file you're transferring. However, we have to be honest here. When you have a short file, such as the gray plot, if you have a 1 megabyte file, increasing RTT severely impacts the link utilization. Also, there are some cases where you have very, very high BDP, where link utilization is very complicated. So this is what I said earlier on. We have a draft so a draft on that specifies an extension to Quick, which is called a zero RTT BDP. What it does is that during the previous connection, client's RTT, the current RTT connection window and client IP are stored, and then they can be re-exploited for the next connection. So here, basically, it is two possibilities and two way this can be done. So basically, the draft that we have describes lots of different solutions on how to do that in Quick. And basically, we are comparing two ones here in this in our experiments. One is using the BDB frame extension, and the other one is using local storage as a server. Both are available in Pico Quick. One has been implemented by Viveris and Franklin and David, and the other one has been implemented by Christian. And basically, so what we have on the top of the figure is the first connection, so the one RTT connection. When you use the BDP frame extension at the end of the first connection or during the first connection, the server store and send connection window RTT in a BDP frame. And when the client reconnects, along with the quick unshakes packets, it sends the BDP frame that the server can use to define or adapt the new conditional window. The difference with the local storage of the server solution is that basically nothing is sent to the client, and the client cannot read the BDB frame and cannot reject it, but still the server can use previously stored conditional window and RTT information. I wanted just to thank a lot all the work on QLog, because that was very useful for us on implementing and checking that what we have been doing was working. So this is just an illustration and just an opportunity to thank all the work on QLog. And basically, you can see here that during basically this is a QLog screenshot, what we can see is the server that sends along with data BDP frame, so that's the red rectangle here, and we can see the red rectangle here at the bottom also when the client reconnects, and basically the conditional window and RTT parameters are exploited in the new connection. So because there are different approaches on how the server can use the parameters. This will be discussed later, and we it could be seen as dangerous to directly exploit the previously measured parameters. So to verify that, we have a satellite broadband system access. And so I have a PicoQuick server close behind my satellite terminal on the right of the figure. The satellite access network, I'm using the GeoCasat with a Pro 25 offer. And so there's a satellite ISP network, which I don't know anything of. And then I have an PicoQuick client instance in our data centers in a server where we have virtual machines that is on the public internet. With OVH provider. And we upload 500K or 1 meg. I don't have enough time to go deep into the details of the results, but basically we have compared the solution of the local storage as a server and the result with the 0RTT BDP. So what we can see from the results is that having basically, if we look at the orange circle here, is that on average, without the 0RTT, it takes us 11 seconds to upload 500K, and it takes less than 8 seconds with the 0RTT and less than 5 seconds with the 0RTT BDP extension. The difference between the 0RTT and 0RTT BDP extension is more on how the information from the BDP frame are exploited. We can see that if we want to be safe, we can have less than 8 seconds, and if we don't want to be safe, we can have less than 5. There's still some optimization here that is required, and we just wanted to highlight the best as we could do if we didn't want to be fair, and we just wanted to take the risk of breaking the internet, which we didn't. Then there may be some question. So this is ongoing tests, and basically I've only run tests on the upload direction. That was strange, and because the traffic was blocked from in the download direction, I didn't know why. I don't know if it was from a server. We have looked at a lot. I don't know if it was my ISP network that was blocking it. We don't know. I could not cross-check the gains because I think most of the gains that we see here is because we have a large TT. The gain with the 0RTT would be less important in terrestrial network, but we could not check that because my home ISP was blocking the traffic in both directions. And anyway, it was safe to deploy as it is because we did not break the internet. And basically, the drafts propose 3 methods. 2 methods are implemented in PicoQuick now and available for any cross-testing. We look for implementers, and we are very happy to anyone who wants to run more results and more tests and experiment with our implementation. We would be very happy to discuss that.
Thanks, Nicholas. I put myself in the queue because I didn't see anyone there. I just have a quick question. This reminds me of in AIX, they used to cache the MTU to specific destinations in the kernel, and you would be able to see them. And there was an issue about how long you kept it for timeouts. I was just curious. I'm not familiar with this work, but I wondered if there was recommendations for how long, whether it's kept locally or whether it's advertised back across the quick connection. How long do you suggest such state be kept?
We basically we do not provide a recommendation on the duration in the draft, but we recommend that anyone who wants to use and to reuse information runs a safety check to see that the performance or the metrics that were measured earlier on are still valid. Basically, the network may change and you may have measured something that is not true now, so you have to check that before actually using previously stored values. And this is detailed in the draft.
Okay, thanks so much. We're already about a minute over. Vidi, if you have a comment, we have a second to do it. If you have a question, can you give it to Nicholas outside the session? Thanks. Thanks a lot, Nicholas. That's interesting work, and thanks for giving us your next steps so we can catch it in the other in the working group. Let's switch to Oliver's presentation. We're just past halfway through our time here, and we've got 2 coming up. Hi, Oliver.
Hi.
All right. There we go. They're coming up. Take it away.
Perfect. Okay. Hi, everyone. My name is Oliver Gasser. I am a researcher at the Max Planck Institute for Informatics in Germany. And in this research, we analyzed MPTCP deployment work together with researchers from IIIT Delhi as well as the University of Munich. So what is multipath TCP? So multipath TCP is a multipath extension to TCP. It allows basically to establish multiple connections between 2 TCP endpoints. It was originally proposed in RFC 6824, which standardized the now called MPTCP version 0. And in RFC 8684, which was standardized in March 2020, this was about MPTCP version 1. So there are 2 different versions in MPTCP. What are some of the benefits of MPTCP over regular TCP? Well, it's higher aggregated throughput, improved resilience, and it can provide seamless mobility in handover situations. MPTCP has been used for quite some time by industry, for example, in iOS devices or in the Siri app by Apple, as well as, for example, by Korea Telecom, to improve the throughput when combining LTE and Wi-Fi interfaces. Recently, MPTCP version 1 has also made its way into the mainline Linux kernel. So everything newer than Linux kernel version 5.6 supports MPTCP version 1. Yet we have found no recent internet-wide study of MPTCP, so that's what we basically did. And we had 2 goals in that study. So we wanted to understand whether how many servers actually supported MPTCP, because that's kind of a prerequisite for clients to make use of it as well. And we also wanted to understand what is the potential impact that middle boxes, so devices within the network that are kind of tinkering with the connection, could have on MPTCP connections. So how did we check for MPTCP version 0 support? So this is version 0. So in MPTCP version 0, the support is declared in the 3-way handshake. Each of the 2 endpoints declare the support using the MB-capable TCP option, TCP extension, actually. Yes. Importantly, as part of this MB-capable option, the client as well as the server both sent their own 64-bit long random key. And that's important because we check for the actual randomness of this key to identify potential middle box interference. So we used the ZMAP scanner to run an IPv4 internet-wide scan. We also did a scan for IPv6 as well, but of course not internet-wide. So when we basically send a regular MB-capable SYN packet, then we get back a SYN-ACK packet with the MB-capable of the target host that we're targeting, and we can retrieve the end host's MPTCP key. And we would classify those which respond with such an MB-capable flag and the key as potentially MPTCP capable. And I will come into a minute because why it's just potentially MPTCP capable and not we're not, there cannot be 100% certainty that these are really MPTCP capable hosts. We conducted a measurement campaign across several months, and we found more than 200,000 potentially MPTCP capable hosts in IPv4, and just a little bit more than 160 in IPv6 over port 443, and a couple of dozen over port 80 in IPv6. So the question now arises: are these hosts that we find, because that's quite a large number, especially in IPv4, do they truly support MPTCP? And in order to understand that, we looked at what kind of middle box interference can happen when establishing MPTCP connection. Well, the first, most basic case is that a middle box just drops the MPTCP connection. The second case would be that the middle box mirrors the scanner's key. So that the key that we send is basically mirrored by the middle box and not chosen at random. The third thing that can happen is that the middle box acts as a real proxy, so using its own random key in the response. And the fourth way would just act as a path-through, which is kind of difficult to detect if done properly. Right. What we can, so in order to understand whether those hosts actually responded with their own MPTCP key, and whether that key was chosen at random, we analyzed the randomness of the keys that we received back. And and if all of the keys were chosen at random, they would follow a normal distribution, and this normal distribution is shown in these plots as the orange line. And as you can see, the IPv4, the keys that we received over IPv4 are on the left side, and those clearly do not, or a large part of those do not follow a normal distribution, as you see the large peak on the left side of the normal distribution. And on the right side for IPv6, there are more hosts actually choosing their keys at random, but we still have a couple of outliers on the left side. And the outlier on the left side is actually the key that we are sending, so they're basically mirroring our key, and that's why we see this outlier.
Oliver, just about 3.5 minutes, so you can decide how you want to spend your next 5 slides.
Yeah. Thanks. All right. So, we can then identify the impact of these middle boxes from. So this already gives us kind of a good indication of how many middle boxes there are using the technique of analyzing the sender's key. But we also went a little bit further. So we used a tool which is called Tracebox, whose goal it is basically to identify middle box interference along a certain connection. And we then classified hosts into 3 different categories. So they either truly supported MPTCP, which means that there was no middle box interference with regards to MPTCP towards a target which supposedly would support MPTCP. The second case would be that we find middle box interference with regards to MPTCP, and the third, we also had a couple of hosts which were unresponsive. And what you can see here is that the number of truly MP capable hosts actually got significantly decreased. So if you remember, initially we had like 200,000 or so in IPv4, and now we have a couple of thousands in IPv4 and just a few dozen in IPv6. Now we also recently started to check for MPTCP version 1 support. Here, as you can see on the left side, the handshake is slightly different. So we needed to adapt for that as well. MPTCP version 1 support, there are 2 interesting findings. The first one being that we again have a very high share of mirroring middle boxes. So middle boxes just replaying the MP capable extension that we sent without useful content. That's the first observation. And the second one is that it has a much lower actual deployment compared to MPTCP version 0. Yeah, so that's basically all. We have a paper which was published recently at the IFIC Networking 2021 conference. There's a lot more in the paper if you are interested in that. So we also analyzed, we did some passive data analysis, and we also have a website, mptcp.io, where we publish regular measurement results. So feel free to check that out. That's all from my side. Thanks.
Very cool. Thanks for bringing that to us. Anyone with a quick question or comment? Oh, Martin Duke's in the queue. Yeah, go ahead, Martin.
Comment. The valence of these different choices that middle boxes can make is actually quite interesting, because depending on the topology, if you're terminating the connection, it's fine to generate your own keys and all that, because if the path then gets diverted around you, then you're kind of doomed anyway. But in a case where something is truly transparent and all the sequence numbers and stuff go from one side to the other, without being modified, then it's generally better to go ahead and just pass on the server's value. So this is kind of an interesting space, and I know the focus is servers, middle boxes, but the different taxonomy you have, like the valence, whether that's good or bad, depends on what exactly that middle box is doing. Thanks.
Sure. I mean, I agree. So there might definitely be use cases or valid use cases or useful use cases for middle boxes that then establish a partial MPTCP connection for part of the path. So for sure.
All right. Thanks so much, Oliver, for bringing that work to us.
Thank you.
Follow up with him directly if you can. I see Jason's up. Jason, if you can bring your slides up. And I maybe I misunderstood. Either you and or 7M are presenting, or you were doing it.
We're both. We're sort of mixing and matching. Great. I'll do some slides, and she will also do some. So hi, awesome. I'm Jason. Can you hear me okay? I think so. Yeah, looks good. So I'm Jason, and my colleague Shebnem will also present, and I'd like to thank her for being up super early in the morning in Istanbul. So we will jump right in. So I think I'm like becoming this guy, like I'm crazy. Broadband performance is not just about speed, but it's about working latency or latency under load. It's really critical to end user quality of experience. And so we've been focused on this for some time. So the background here, and Shebnem will go into some of our results in a moment, but we had a really fortuitous set of events that came together here just prior to the onset of the pandemic. Really in January of 2020, we rolled out a CPE-based measurement system to millions and millions of our cable modems, and that includes a latency under load test as well as a whole suite of other tests. And we started running about 700,000 tests per day. So one really nice part is prior to the pandemic, we basically were creating this sort of baseline measurement to see how the network was performing, and in particular how different cable modems were performing. And then shortly thereafter, we were actually working also on AQM deployment. So it's a baked-in feature of DOCSIS 3.1. It's a mandatory feature, but we had one particular variant of a cable modem, which we called the XB6, that didn't sort of have AQM working right, and so it was turned off, and the other variant had it turned on. So from a measurement standpoint, it was really wonderful because we had this great control group with AQM turned on. We had an experiment group with it turned off, and so we were able to at some point then turn it on the other set. But we're basically had two variants, the exact same hardware specification, just from two different manufacturers. And so really a very interesting apples to apples comparison was possible. So it was great to then, in a way, from a measurement standpoint, I suppose, to see everyone move to work from home and learn from home with all of the attendant network demand that happened at that time. Really created a perfect laboratory for us to study these things. And so we had many tests run. And on the next slide, Shebnem, if you can speak to this.
Jason explained we had two DOCSIS 3.1 modems, and one had AQM enabled, which is the orange line on the graphs, and the other one had AQM disabled, which is the blue line. So these graphs show the cumulative distribution function for the working latency under load. displayed in millisecond on the x-axis. And here we have mean and maximum values, but we have a new platform that includes other percentiles and also the transaction rates to estimate the packet loss as well. So what we can see here that when the AQM has been disabled, we had really cases where we can see buffer bloat, and obviously it would affect the quality of experience for many sensitive applications. So our main goal was to assess the latency in our access networks between the cable modem and the CMTS, and optimize the active queue management settings to improve the latency and jitter. But we also made sure that the throughput and the packet loss requirements were met. So we tested and monitored all these quality of service levels. And we also collected gateway metrics, customer calls, tickets and track rows to make sure to confirm that the latency and jitter improvements we deployed did not create any other quality of experience issue. So this data show that, I mean, for these graphs, we use bidirectional latency load. In both downstream and upstream, we had TCP loads. And we can also see the impact of downstream TCP load on the upstream TCP acknowledgements. So we can see the downstream load increases the latency for the upstream traffic. Before we deployed our latency under load working latency platforms, we validated the test parameters because the speed test is more widely known, but the test parameters that are optimal for the speed test may not be optimal for the latency, because the TCP data may not fill up the queue, even though they may fill up the full speed TR rate. So we analyze our cable modem and CMTS buffering architectures and compare our results with the latency test to make sure that we can optimize the parameters. And we want to have the optimal values within a short duration, because when we deploy these tests at a high scale, we don't want to have a big impact on the network load. So it's very important to have an accurate latency measurement within the short duration. So it's important to have a common and accurate way, a defined way in a standard approach. Another challenge is that we started to measure the latency for higher speed TR rates. We are trying upstream rates at 1 gigabits per second or more. So these high-speed TR rates have other challenges when we want to have an accurate working latency measurement. So this is why it's important to define a common platform that can work for different speed tiers, network architectures, and also different configurations.
Sebnem, you got about 2 minutes, and you have one question in the queue.
Yep.
Yeah.
Great, thank you. So moving on, I think we saw obviously dramatically lower working latency as a result of turning AQM on, and it was obviously really great to have this large-scale measurement system in place, really just before we did all this stuff. So that was great. Certainly, our recommendations are, ISPs and equipment makers should continue to deploy AQM. But it also struck us as we went through this, and especially as we were working on the measurement platform itself, that while there are some standards around things like speed tests and these things, when you look at how people have implemented this in the wild, whether it's SamNose or Ookla or Fast.com or whatever, these are all wildly different, and so it makes it very difficult to compare across tools because it's unclear sort of what standard or specs they use, what variables, and so on. So it seems like there's an opportunity for some standardization there, and then of course that makes possible eventually data sharing and comparison. So I think that's it. There's of course a longer paper that you can click on there, the second link, and you can read more about the measurement system itself in the 2 top links. So happy to take any questions.
Thanks, guys.
Thank
We have Jonathan Morton in the queue.
One comment from my side quickly. This is a good point in time to remind everybody again about the IB workshop.
Yes.
So this is exactly how measurements, so consider setting something there.
Okay, so I wanted to ask to confirm exactly which AQM is in use at each end of the connection, both at the CPE and at the head end, and whether ECN is enabled in each of those.
So for the cable modem, the AQM method is the DOCSIS 5 defined in DOCSIS 3.1 specifications. So both cable modems have the same implementation defined in the specification. We also have some CMTSs at the head end that have their own AQM, so they have their own proprietary codes, not per specifications. We also optimize their values. So it depends on the cable modem versus CMTS model, but the main part of the AQM is the same. And that was another question, I think.
Yes, it was whether you had ECN enabled.
So for these AQMs, there was no ECN. Like, for example, if there is congestion, there was no CE marking, but we are working towards an AQM that can have ECN capabilities.
And also making sure we're not bleaching ECN.
Yes. Yeah.
Okay, we're about at the end of time. Let's take Al's question. Thanks, Jonathan, and then we'll wrap up the session.
Thanks. Thanks both of you for sharing this data with us. My question has to do with the test stream that you used defining working load. I think that's going to influence the results a bit, and maybe you can describe it briefly. Thank you.
The current platform that we are using uses Maprg 3 for TCP load, and then Maprg for UDP ping latency measurements. So this is the current protocols that we deployed in our network, but we are working on some new platforms for higher speed TR rates. They are not finalized yet. But Maprg 3 and Maprg with cubic TCP are the current protocols we deployed.
And that does point out, I think, as well, like, we were sort of experimenting a little bit with what we arrived at, and I don't think there's a lot of great knowledge about what the right thing is at scale.
All right, thanks, Al.
We can talk about maybe in September. Thanks.
Yeah, thanks, Edna and Jason, for bringing that work to us, and thanks again to all the contributors. That's our whirlwind meeting at the end of an IETF week. Have a good weekend, folks, and join us next time.